Hello, boys and girls. So in this small comment, I want to contribute with some graphics that I made and I have never seen before that explain certain transformation relations for the Lebesgue integral. So we have some examples here on the screen. So when everybody knows if you have a function which is integrable over the whole real line, you can of course shift the function on the x-axis. Then you will get the same out of it. This is basically very visually clear. If you just shift the function, but you're still integrating over everything, you will get the same thing, right? So the first thing is the default go-to translation invariance. But also more interestingly, and this is known as like the main case of Glasser's master theorem, where there are some YouTube videos that use it, and I found one that even does proof more or less of it online. We are actually like, I will show a proof at the end, this, at least a proof sketch, and also of the generalizations. But I want to visualize actually what's going on there with some graphics, and this is what really the video is about. So yeah, indeed, if you have a function where the integral from minus infinity to infinity is some finite value, then it will also be a finite value and the same finite value. If you do this dangerous looking transformation, right? So we do not just shift this by a constant, but we actually have a non-linearity in there, and the non-linearity even has a pole. And the claim is that the outcome is the same. And what's more, once you have that, you can play around and play with the offsets and put some constants in there. It turns out these constants don't really change the integral either. And so you can integrate over a general transformation u of this form, and it will still be invariant. So I hope this is not too small to read, but this is basically x plus an offset that we already had, minus, and then there's a sum over these fractions where you have a positive number, any positive real in the numerator, and then x minus, and then some zero position xn, and you sum up a finite number of those. These are like distinct points on the real line, and the claim is that the integral does not even depend on all these numbers. They are just kicked out, and the integral value actually stays the same. And what's more, even you can, and this is a case that I will not discuss formally in this video, but if you put some constraints on the sequences cn and xn, the zeros, then you can even go with n to infinity. You just have to avoid accumulation points of these sequences and have some mild integrability conditions. And one application, the tangents has actually this form, and so it turns out that if you have some Lebesgue integrable function f of x and integrate over, you can actually add 10x and it will not change. I ran across this on the weekend because it was like posted on X, and there were like so many surprised faces for this relation that I thought maybe it's worth putting on here. Okay, so the contribution I want to do is like a visualization where it sort of becomes very viable that this works out, and then I have some small technical analysis of the thing as well. So right, I mean, at least this finite case, you can buy into it once you have bought into this transformation, right? X minus 1 over x, that's the main thing. The constant, scratching and squeezing, you can believe, and then once you have this, you can do this a finite number of times, you will get this invariance also out of it. So what remains to be motivated is this sort of relation. And I will show some Wolfram Alpha graphics, which basically show you why this works. Basically, why this transformation as a transformation of the real axis does not change the measure of Borel sets of intervals. I mean, I will show it for intervals, and the image that we have here is as follows. So Here you see, in this case, I start with just the interval from 0 to 1, right? So I imagine an interval which goes from the x-axis value 0 to 1. All values in between there are relevant. This thing has, of course, the length 1. You can, for example, and we will get to this, you can think of f as a characteristic function which says 1 in the unit interval and then is not supported anywhere else, is 0 everywhere else. And then if you do this transformation, if you plug in characteristic function of this expression of x, then that's what I do here, right? For all these values that where this box is supported, we plug in this expression for some arbitrary y, right? Let's say y equals 2. Then what we get out of it is this. So here I can fix a y value, for example here y equals 2, and then what we see here is all the x values such that the image of this transformation is exactly in this box from 0 to 1, right? I mean, as per definition of what I'm looking at here. And what we see here is that this interval of from 0 to 1 is split up into 2 parts, right? So all these values, which if I scroll down, they go from roughly, I would say like roughly around minus 0.5 to 0.3 or something like that. All of these values, they will be mapped into the unit interval by this transformation. And then there's some other interval here, which are also values that are mapped into this, right? So this transformation splits up the unit interval into 2 parts. And if, for example, we have f being the characteristic function of the unit interval, the integral over it being just 1, right? It's 0 all the time. Then there's this rectangle. We integrate over it, we get 1, and then the rest is also 0. Then how this looks like is as if there were like 2 characteristic functions on 2 new spots, 2 new places here. And it just so happens to be that the length, if you add them up from here to here, from this left end of the bigger part to the right end, and then here to here, this just is again just 1. So this was actually a unit preserving, a measure preserving transformation. And you can see this here. Like I plug this into Wolfram Alpha here, right? I have this x and y general, and I tell it solve this, right? Give me the access such that this works. And what it returns is like it basically tries to find the left bound and the right bound, right? For example, this bound and this bound and this bound and this bound, such that the x lie in between. So we have a bunch of ugly roots. But if you look closely and see, okay, what is the length from here to here plus the length from here to here? Well, it's this upper bound minus this lower bound for the first, and then plus this upper bound minus this lower bound. And if you compute this, right, you can just add the positive things up and subtract the negative things. And then you will find this and this exactly cancels. Here, the square roots, they just fall off. And what you're left with is exactly a unit 1. And if you choose another y, right, you see that the situation stays the same. I made another plot to visualize this, like this box situation here. So here we have this characteristic function is here drawn in orange. You don't see it fully because there are so many colors. But it basically is 0 till 0, then it's 1, then it's 1 till 1, and then it goes down. If you integrate over, you get, of course, the volume, which is 1. And then what I also plot is, I mean, of course, this blue line is just literally the transformation drawn in the same plot. But then the dashed green line is box of this transformation. And we see, of course, the question is, hey, where is the transformed value between 0 and 1, right? Where is the transformed value here in this interval? And what are the x values where this happens? And since this transformation splits the real line into two parts, right? You have this left branch where it goes from minus infinity on the y-axis to plus infinity. Then there is the asymptote, and then it goes another time from minus infinity to infinity. You can see just in the picture that the x values here and here are exactly these new split x values, and I will give you like a more formal analysis of why the sum, like this, if you sum up this length and this length, then you obtain exactly 1, which is also the length here. Okay, so I did this with general y, and I get this nice contour plot. In the next picture, I plug in 1 for this y, but I also add another. This is not it yet. Yeah, I also plug in another term. So here's x plus 1 over 1 minus x plus 1 over 2 minus x, right? And you can play with the signs. You can also say x minus 1 over x minus. This is just a simple algebra, but it's the same transformation, but now with like 2 terms. And you see that this thing again makes me a drawing. Now I cannot really do it in 2D because I plugged in these hard numbers, but you get 3 intervals that you see here, right? So it's just split up more, and you can do the same computation. Hey, was this actually measure preserving? And it turns out to be yes. I actually did this by hand. I just wrote down the numbers, summed them up, and it comes out up to noise, numerical noise, as 1. Yeah, for your convenience, you can also, as always, look in the text that post below. I have the links to all of this kind of this simple Wolfram code. What I do here is I go back to the first case with the y, but I actually add now a c at the start, like the beginning of the interval, and then d with which you can tune the end of the interval. So basically now I let the endpoints free, and I don't restrict myself to length just 1. And if you do the same calculation again as before, right, you sum up the endpoints, subtract those, then you will see, oh, the length is exactly, I don't know, whatever 2D minus c or whatever comes out. Now 2D, I think 2D is in this case the length. Okay. Yes, this last bit before we go to the sort of mathematical proof is just as a visualization right here. I just want to highlight how here you have this 1 over x with a little bit of an offset. I argued that the tangent function is also just the sum of those. With the tangent, it's basically an infinite sum. So you have actually like infinitely many of these cuts. But things still work out the same. It just happens to be that the Jacobian in this transformation is just much more complicated. But in the end, it's basically just an infinite sum of the same sort of real simple poles. Okay, and so to wrap this up, I will give you like the a little bit more formal than at least that I've seen in other videos, like analytical argument, why that checks out. So here we have again, I do it in this case for this like raw simplest Glasser transformation case. I argue this is leaves the Borel measure invariant. I've already shown you the graphics, and so here this short argument. So of course the real line splits into 3 parts with this transformation. We have the negative x-axis, we have the 0 in the middle where the asymptote is, we have the right axis. The singleton in the middle will not be relevant for an integral if you integrate over functions. It has a null measure. And so to integrate this any function, you just have to compute the left and right part, right? You can, in any case, apply the generic transformation rule for these integrals, which in this case, it's just scalar functions. It's just 1 over the derivative and then all the correct values on the x-axis. Of course, in general, this is the Jacobian, and then there's 2 inverses. And now, I mean, maybe it helps again. This is something else. Probability exercises. Where do I have this image? Here. Jesus. Here we have again this image where we had here the asymptote, right? And here you can also like read off which parts are going to be relevant, right? So for x-axis, the negative values, you will go still from minus infinity to infinity just to catch the values on the negative x-axis, and you will go from minus infinity to catch a positive axis. So basically the transformed interval, for the transformed interval to catch all the values, you have to, if you integrate over the y-axis after substitution, you have actually to do two integrals and go in both integrals the whole line, literally line, right? This is this here. And in both of those, you will use the transformation rule. The derivative of this function, I mean, this is just x minus 1 over x, right? So you can explicitly compute this. This is this thing. But then you have also to do the inverse, and the inverse now splits into two parts. For this part, from minus infinity to 0, you use the one inverse, and for the other. And if you write this down, since this is just this simple expression, and you say, oh, for fixed y, what is x in terms of y? You just solve a quadratic equation basically. And you get out these solutions. Here in this equation, it's a little bit sloppy. I wrote both solutions in one equation, but I denote them with plus minus. Here you see that this should probably be a 1. Yes, so I've written y here, but it should be a 1. The point is that if you take both of those Jacobians and sum them together, you get 1/2 plus 1/2, and you get a constant. This is sort of the magic that happens. So disregard my typo here. And so if you do this for both sides, you get similar Jacobians with different signs. They cancel out, and this integral just happens to be the same as it was before. And yeah, so just as a note, if you do for the finite case with more terms, you would have a longer finite sum of these Jacobian terms. And then if you go to infinity, you technically have like an infinite term. And to do this property, properly with this limit to infinity, how this is actually done is that people look at contour integrals or whatnot, but I don't do this here. Already at 20 minutes. I do not know of these nice contours and so on. I've never seen them anywhere. So I hope you learned something new here. There's a Wikipedia page which is by far not as complete as it could be. It talks about this finite case, and this talks about principal values still, but for many functions, for the Lebesgue integrable functions, this thing, like if you do more work, you can drop those and get to nice transformation which converge if you have the right constraints to make it as I showed.